Okay, here are two more IR unknowns, infrared spectroscopy unknown compounds. When I look at this spectrum, first thing that pops out to me is this peak right here, and it looks like it is between 16 and 1700. Now, an alkene shows up at about 1640. So when I see something about halfway between 1600 and 1700, I'm thinking an alkene is very likely. Let's go to our table, though, and find it. So as it turns out, we have a peak at 1651, has an absorbance of 15. It's a pretty small number, meaning this is a pretty intense peak. And so this looks like an alkene. So I think it's pretty safe to say that we have an alkene in this molecule. We don't see anything past 1700, so there are no carbonyls. That's typically nice to know. And then, we have something here. These look like sp3CHs since it's a peak just short of the 3000 line. Now notice we have this sharp peak, which is just beyond 3000. And short peaks beyond 3000 tend to be sp2CHs. Now where would these sp2CHs come from? Well, alkenes contain sp2 hybridized carbons. So our alkene probably has 1, 2, 3 different CHs on it, and we're seeing evidence of those sp2 CHs just as we see sp3 CHs. Now we have one more peak right here. This is just beyond 3000. What is this? The IR picks this up as two separate peaks, both a little bit past 3300. And this is broad. This looks like an alcohol. Now, I confess that if you're new to IR, it's easy to look at that and say, wow, that's not just broad, pal, that is very broad. But, and when I say that things are very broad, I'm normally thinking of a carboxylic acid. But it's not an acid, and we know it's not an acid because a carboxylic acid would have a carbonyl absorbance at about 1720-ish. And we don't have a carbonyl in this spectrum because the only thing we have down here in that region is what looks like an alkene. So this looks like a molecule that contains an alkene, and it looks like it contains an alcohol. And again, that's about all we can put together based on the IR. If we want more information, we can go to the mass spectrum or the nuclear magnetic resonance spectrum. Okay, so let's see another example. Here is a molecule. Oh, this region right in here. If you have anything here, normally it stands up because nothing shows up in that region. So we have a peak. Where is that? It's around 2100-ish. So let's find it exactly. 2120 is our peak. It's a weak peak, but still it sticks out. If something is less than 2200 in here, that's typically a sign of an alkyne. So I think we have an alkyne in this molecule. Now, alkynes, the spectrum is a little less clear here. I'll pick out the easy stuff. Here's about 3000, less than 3000. This looks like sp3CHs. We're going to see that in just about every molecule, so it's not earth-shattering to say I see some alkyl CHs because they're in almost every molecule we see. One thing you'll notice that this is a fairly broad peak here in about the 3400 region. This looks like an alcohol. There's no carbonyl around 1700, so this is an alcohol, not a carboxylic acid. For an acid, I'd expect it to be broader, but this looks like an alcohol. One other thing I'll note is that this isn't a simple alcohol. This got this pointy thing on the end. What is that pointy thing? Well, with an alkyne and a sharper peak around 3300, which is this tip here, this looks like the CH off of our alkyne. So that little point is further evidence that not only do we have an alkyne, but it looks like a terminal alkyne, where the alkyne is on the end of the chain. So this molecule looks like it has an alcohol. It almost certainly has an alkyne, and that alkyne itself is probably dangling off the end of the chain. So it's not, we don't have the alkyne sandwiched between our groups. We have an alkyne that's on the end of a molecule. And again, that's about all the information that we can get from the IR spectrum. It doesn't tell us what the molecule is, but it does tell us what functional groups are present in our molecule.